Welcome, my name is Owen Redwood, and this is part of the 2015 version of the Offensive Computer Security OpenCourseware, hosted at hackallthethings.com. In this lecture, we're going to be bug hunting with source code, specifically in C and C++, and going over various security auditing techniques that one might employ. The outline for today's talk will go over several important topics, including CVEs, CCEs, CWEs, strategies for bug hunting with source code, common developer errors to look out for, and finally, some examples with vulnerabilities in them for you to do in the lecture with me giving answers afterwards. Some of them at the end have no hints and are more realistic. To provide resources for today's talk, one should consult the following links for CVEs, CWEs, and CCEs. We're going to first start off with this interesting document that's put together by MITRE, which is an effort to categorize all the types of weaknesses and vulnerabilities into 7 kingdoms or categories. Now this document is pretty large, so we'll zoom in. The top level kingdoms are here on the left, with it just representing root as that on the left. And from top to bottom, they view Kingdom 1 as input validation representation, which covers weaknesses like buffer overflows, integer overflows, as well as web application topics like cross-site scripting, command injection, SQL injection, and so on. Then the second kingdom is API abuse, which covers misuse privilege management, unhandled exceptions, improperly used authentication, and so on, or use of dangerous functions like strcpy, which we've covered in previous lecture. The next one is security features, or improper security features or weak security features like poor randomness, violation of the least privilege principle, or missing access controls, poor password management, and so on. Time and state covers things like race conditions. Error handling covers exception handling, perhaps done poorly, which may expose use after freeze. However, they're not in this category. The next category, however, handles them, which is code quality, which covers things like double freeze, memory leaks, null dereferences, undefined behavior, use of uninitialized variables, use after free bugs, and etc. Encapsulation is the next kingdom, which covers object-oriented topics as well as mobile code, which I assume means for phones and tablets and etc. And can involve type confusion depending on the circumstance. And the final one is environmental issues, which range from setting up your compiler wrong or perhaps with the wrong flags to misconfiguring environmental settings like .NET. It might also involve the web server, the database, etc., and so on. Go back to the lecture now. A very important resource that one should at least be familiar with if they're getting into security is the National Vulnerability Database. Now, it's not something you really want to troll through every day, but it's worth visiting. So we're going to go through this example and a couple other examples and see what's new for today. This is the NVD entry for the given example. Its identifier is CVE 2012-0861. The first number always dictates the year in which the vulnerability was disclosed and processed by the organization. There's several organizations that collaborate to maintain this list. Both DHS, US CERT, and MITRE are some of them. There are others. I'm not aware of the entire list, but they all followed the same format. They covered the release dates and the source that it came from. Sometimes the source will give credits to the author who found the vulnerability or the person who reported it. Um, and the overview covers a kind of high level description of the impact of the bug, the attack vector, and other details. So this covers Red Hat Enterprise Virtualization Manager. It specifies the version, specifies the environment, and the conditions in which it applies. And the impact is that it allows remote attackers to execute arbitrary Python code via a man-in-the-middle attack. The impact has a number of scores. The impact subscore is usually the one that's paid most attention, and this is a 10, which is the highest as far as I know. The access vector is described, access complexity, whether or not authentication is required to exploit the vulnerability beforehand is described, and that is something that is prevalent at least in web applications, say forums, content management systems, and etc. There's certain aspects and actions you can't perform unless you're a logged in user. So there is some form of authentication, even if it's just a bogus dummy account, then one can register freely. That must be done before exploiting the vulnerability. Finally, the impact type enumerates what possible impacts and damages there may be, such as unauthorized disclosure of information, unauthorized modification and sabotage, and disruption, denial of service, etc. Usually, after that, there's remediation or patching strategies, as well as a list of a bunch of other advisories that pertain to this vulnerability. So there are identifiers other than just the CVE list, and typically each organization, in this case Red Hat, but in other cases Google, Mozilla, Apple, Microsoft, and etc., will have their own identifier numbers, and they serve as advisory lists for their own customers. So at the end, there may be links to exploit code, like repositories like exploitdb, where one might find publicly released exploit for the given vulnerability. However, there is not such a link here in this case. Let's quickly glance over the top vulnerabilities for today. Here, it will typically show you what the nature of the exploit or the vulnerability is. Here, the vulnerability in the McAfee Enterprise server is a bug that allows remote users to execute arbitrary OS commands by crafting file names for those commands, and it handles them improperly, which is, in a sense, command injection. Here, use after free vulnerability is found and disclosed in Adobe Flash Player. Similarly, Flash is again hit by a couple more, one being a buffer overflow. Here is, unsurprisingly, arbitrary remote code execution. Typically, when that's described, there's already an exploit to demonstrate it. And perhaps Adobe is holding any more details, so then it is described as via an unspecified vector. And however, it is noted as different than the other vulnerabilities that for it have been announced today. Again, another buffer overflow, and so on. Stack-based buffer overflow this time. At any given time, you will usually see some Oracle, Adobe, or similar product, maybe sometimes rarely Linux, taking up the majority of the notices per day. Again, all of these but two were vulnerabilities in Adobe Flash. I guess you could say it wasn't a good day for them. So back to the lecture. Some more details on CVEs before we go on. Again, the goal here is to make it easier to spread and share all of the security information about specific vulnerabilities. There may be dozens of ones that get dumped per day on a single product, which can make it confusing if we didn't have this scheme to, in such a case, describe and communicate these problems. And this is run by MITRE, and it's working with a number of U.S. government groups that are all white hat and doing this to help us all out. That's a noble endeavor. It's also something that should be taught mandatory on all software engineering classes. Like all intro to programming classes should cover this. Um, and the definitions that they list are worth going over. So a vulnerability here is described as a mistake in software that can be directly used or abused by a hacker to gain access to a system or a network, or a resource, such as like passwords, database records, and etc. Exposure is a mistake in software that allows access to information or capabilities that can be used by a hacker as a stepping stone into a system or network. So, like a database exposure, um, say they're just going after credit card numbers and stuff like that. They wouldn't necessarily be using that to log back into the target network. They'd be using that in a separate attack or a separate stage where they're trying to profit off of their loot by charging money to those credit cards, obviously fraudulently so, in order to get rich. So there's some lacking in the definitions, but they're good enough to get started. Um, so next, CCEs are common configuration enumerations. As I described, they detail how to properly configure certain technologies. Usually, they're provided for the general case and not don't provide specific guidance per version, per product. For all the distinct products out there, there are just simply far too many. But for simple administration of systems, there's plenty of them, ranging from operating system tips for Linux, Windows, Apple, Solaris, and etc. And anything ranging from how many password attempts should be allowed, what the permissions should be on certain system folders, the password retry attempt should be, what format to encrypt or hash passwords in, and etc. Fairly useful stuff, but I haven't gone through it all myself. Now, CWE, is an attempt to enumerate all the possible weaknesses that may lead to a vulnerability. And so, this is more of a textbook-based approach with sample code and descriptions on each bug category that they have attempted to enumerate, ranging from buffer overflows to format string vulnerabilities, and etc. I've found in practice a bit of redundancy in a number of the CWEs, though. Some of them are a bit broad, like GUI errors, authentication errors. Some of them are a bit specific, but in general, across all of them, they vary wildly in the specificity of the CWE, which is a bit of a problem that there is with them, but it's not a big problem. Anyways, at the end of this discussion, I wanted to note that weaknesses are a subset of bugs, and this is something you should be able to recreate at any given time. Is that for all sufficiently large code, some part of that code are bugs. Not all bugs are exploitable, and not all bugs are security problems. Like displaying something in the wrong font, wrong color, could be a bug, but it's not going to be a problem worth prioritizing over something that could be a serious vulnerability that an attacker can exploit to affect your customer base, affect your business, and affect other factors. So for all sufficiently large programs, there's going to be bugs. Some subset of those bugs are going to be weaknesses. They may individually or a combination thereof lead to be vulnerabilities. Some of those may be exposures, but not all vulnerabilities will end up being exploited. Only a fraction will ultimately end up being exploited for various reasons. Um, the difficulty and exploitation of this set of bugs may vary wildly as well, and attackers typically go after the low-hanging fruit. There's no reason to tackle a when you have two vulnerabilities, one's going to take you a day and get you access to the system versus one that's going to take you 100 days. There's obviously no reason to go after the harder one. And so there are numerous factors that lead to the difficulty or the mitigation of their exploitation, which we'll go into in the exploit development lectures, such as exploit mitigations like ASLR, DEP, stack canaries, cookies, and other permissions and mitigations. But I digress. There are three primary methods for discovering vulnerabilities that we will cover in this class. However, there are definitely more, as we will cover in the advanced bug hunting and vulnerability research lecture. But today's topic is source code auditing, and obviously that requires source code.
And at the end of the day, source code auditing is very tedious and time consuming. It's very hard to estimate the cost and how much time it's going to take. And it's largely, one's ability to do it is largely dependent on their knowledge and skill with that given language. And there are many tools that you can use. The most important one is going to be the source code comments left by the author. If you are given the task to audit a large amount of code and has no comments, I pity you. That is terrible. It's really a nightmare to deal with for sufficiently large code. But hopefully you are given code comments, and then you're able to use tools like your favorite source code editor or reading tools. Then that invokes the VI, Vim, Emacs debate. And then there's pattern matching tools and regular expressions. grep finds bugs if used properly. We will cover that in just a little bit. There are static analyzers. There's lots of software out there, Coverity. I can't remember all of them, but they are sometimes prone to false positives. They largely use regular expressions and are essentially what are considered the old term expert systems. It's effectively a group of people that were really good at finding bugs by statically looking at code and writing regular expression rules to match when code looks like certain cases and then making you aware of when it does. But lastly, the tool that I find most useful and people I know find most useful is pen and paper. It is going to be the most useful thing. You don't want to edit the source code when you are auditing it. That's usually a no-no. Even if you're adding comments to it, it's better to take notes on a piece of paper so that you aren't changing lines of code, because if you find a bug and say line 512 and you edit line 400 to add 3 lines of comments, that can cause problems on how it's later looked at from your notes and can lead to confusion. Which leads us to, now that we've covered tools and the different categories of bugs, what your approach and what your goals and what your strategy should be. Are you focused on finding the most bugs? Because all software contains bugs, and for all sufficiently large software, there is actually a point at which there's increasingly diminishing returns that is not cost effective to continue finding more and more bugs. Do you want to go after the easiest to find bugs? Do you want to go after perhaps weaknesses that are the most reliable to exploit? That's usually a rewarding goal. But at the end of the day, the message is that it is very important to limit the approach because you will never have enough time for a sufficient large project to find all the bugs. It's, it's just not feasible and it's not cost effective. Thus, it is important to prioritize in general vulnerabilities. So my general methodology to bug hunting with source code is first gain some understanding of the application. This is kind of a cyclical process. Second, to understand the attack surface and the ways in. And then third is to target your efforts accordingly. So really, at the end of the day, this all involves not just reading source code, but reading documentation, reading specs, and reading what other documents you have available other than just the plain old source code. Things like web page, the features that are advertised, and what the selling points are. Those are obviously the important features. Understanding the programming language is paramount. There is a division among basically the people available that do source code auditing well. Either they're good at auditing the classic binary source code, uh, I mean the C, C++, C Sharp, Java, etc., those languages, or the web architecture auditors, the PHP, now up and coming Python, JavaScript, etc. auditing. After, well, I guess hopefully you're familiar with the target language, then you want to focus on what features there are and perhaps look at the more complex ones. Because I've found that the more complex something is, the more likely a developer did it wrong. Um, and then you want to focus on the components. And that comes down to really the architecture of the application. Application may be an operating system, it may be a website, or maybe an MMO client, or video game, something like that. Maybe your tax software, maybe a text editor, or a intrusion detection system. So for a website, the clients, the customers, the users obviously have a web browser, and they look up your URL, and it does a DNS search, and it provides your browser with an IP address, and you connect to that, and you connect to the web server, and it's usually behind some sort of firewall if the people want any chance of it not getting hacked. And behind the firewall, that web server may be interacting with other services that may be on that same physical machine or maybe on other machines in that network, such as a database or some form of access control service or an authentication service. And now more and more actually nowadays you're seeing login with Facebook, login with Gmail, that obviously is not done locally at that service. They have to outsource it to Gmail, Facebook, etc. So that goes back out over the internet. So that's if you're trying to understand the architecture from the company's perspective, that's another way into your network because you're going out to the internet to that third party, and you're relying on a response from that third party to tell you whether or not this user is authenticated. Now, say for massive multiplayer online game. You have users that have MMO client. Maybe you also have different set of users that have administrator or game master privileges, or perhaps they're testing out the next build, sort of a beta test, and they may have different features and accessing different APIs other than the normal customers. And so again, it's all coming in over the internet, and the game server or cluster of servers may be coordinating with a web service to provide account management, stats, and stuff like that. Maybe coordinating with a database to keep track of all those stats and have some form of access control. And usually they don't do all the billing on site. It's at the end of the day, it has to be passed on to credit card handlers like Visa, MasterCard, and etc. Perhaps even PayPal, and increasingly we're seeing with Bitcoins. And there are actually been a number of vulnerabilities in Bitcoin websites attacking wallets with cross-site scripting and whatnot. Or perhaps it's a application that really doesn't do a whole lot other than spam you with you need to update messages every time you start it or something like that, um, like a image editor or viewer or something like that. Um, and you contact the master server, and there's an update service and perhaps a CD key validation service. And you have to really understand the architectures of these different, of your particular scenario to really do code auditing effectively, because the architecture dictates the attack surface. And the attack surface is what attackers are focused on. And the intersection of the attack surface and the potential goals that an attacker may have should drive your code auditing efforts. If you're more interested in protecting against sabotage like website defacing or attackers destroying all of user data, which would really affect services like Instagram and Dropbox. If you logged in and all of your stuff was gone, there was no way to recover it, or perhaps in the case of Dropbox, that was your backup solution. Or perhaps you're more interested in protecting against users from maliciously gaining access to perhaps exploit a free service, or not necessarily on your servers, but perhaps on other users' machines, which might lead to the creation of a botnet, or perhaps identity theft, or attacking or harassing actual users, or perhaps you're interested in piracy and theft and preventing that. Really, the art of understanding the attack surface breaks down into four steps. Is you have to understand the inputs and the outputs of the architecture, and you have to understand the inputs of the application itself, because those dictate the attack vectors, usually for exploitation of that application itself. And you should really prioritize the inputs of an application that have remote accessibility, because vulnerabilities and those and the resultant code paths or derivative code paths from those inputs usually have a much higher impact vulnerability-wise. And things like authentication mechanisms are another good target to prioritize. Perhaps the credentials are communicated between the client and the server in clear text or in a stupid encoding. So back to remotely accessible code paths. I define it as functions or features that can be executed as a result of network interaction or input. The thing about code paths that are not remotely accessible is that they are not likely to be remotely exploitable. So things that are run on startup, or in a constructor's code, like reading a config file or loading config settings or initializing things, those aren't likely to be in most settings triggered as a result of network interaction. So then the next overall step, now that we're done with understanding the attack surface, is targeting your efforts. And I like to target your efforts by thinking like an attacker. And there's some overlap here. Is relate the input sources to the application, to code paths, and examine those if you have the source code, and see if there's any vulnerabilities you can find there. That happens to be one of the most effective ways to do it. also to target important components, and that requires understanding the architecture. So perhaps there's a database, and you might be able to do meta-character injection, perhaps pull off some SQL injection at the end. Um, and then I've always found that the more complex the thing, the more likely it is to be implemented wrong. So things that are complex to parse or very complex protocols or functions usually are more rewarding to look at when finding vulnerabilities. So if you have, as an attacker, access to the source code, like many open source projects, you can perhaps download the repository of source code from Git or the SVN server or wherever it is hosted. And I've actually found ODAs by grepping for things like XXX or bug or vulnerability, and it's basically bad code that the developer never got around to fixing, but they just commented that this might lead to a buffer overflow, or XXX, this is weird, or I don't understand this. Another good good thing to search for are curse words, actually, or perhaps typos of common functions. Um, and usually you'll find cursing in comments if a developer is really angry at something, has been spending a lot of time trying to get something to work or get something to compile, maybe something really complex, and they finally got it to work, and they just commented F this, or we'll get back to this later, or sometimes it causes a crash. In the other cases, it didn't take them that long to get, but they could never reproduce it reliably. And so they may comment somewhere in the neighborhood like, this causes a bleep bleep crash. I don't bleep and understand. Um, Another thing to search through is old code and old libraries, things that were checked in a long, long time ago, because those may themselves have older coding practices or may be using APIs in a non-updated way. Another good strategy is to look at the check-in date. Look for code checked in after midnight, like after 4 a.m. The probability for most people of checking in bugs actually drastically increases, I've heard. It's not an empirical or a scientific observation, I'll add. But we'll see later in the semester when we discuss web security and SSL. Moxie Marlinspike interviewed one of the lead designers of SSL, and he said it was largely a 4 a.m. decision, which is pretty funny. Um, Also look for code checked in by, if you happen to find bugs by one developer, like systemic bugs by one developer, look through his other stuff, and perhaps also, if it's a large amount of code, just target code checked in at the same time as the other bugs, and look for patterns from that buggy code or stuff like that. It's really preying on the weak, a lot of these strategies, but it does pay off. Now, the outcomes of using these strategies, I will leave to your own conscience. Hopefully it doesn't lead to getting good people fired, because if you clearly pick on one developer over and over and over and over and just find bugs from one developer, either he's going to get fired, he's going to beat you over the head with a $5 wrench, or something else is going to happen in between, I bet. So, on a different note, reading code is obviously really frustrating at times, and it's important to skim past filler code, but also to be thorough. Filler code includes things like macros or initial or hard-coded value assignments, function prototypes, stuff like that. Some header file stuff, but that can be important sometimes. And it's important to, in your thoroughness, to read iteratively, to understand each component as you observe it, to gain a more complete picture of what's going on overall. And there are some tips I found from IBM, as they have a large amount of developers and are able to do empirical evaluation of um, code auditing rates, lines of code right at a time, and pace, and etc. And they found that reading fewer than 200 to 400 lines of code at a time is actually optimal, and you get significant diminishing returns, and you miss bugs if you read more than this. And at a time is really dictated, I guess, by a sitting, and so they judge that faster code review is not better, kind of is redundant in the first point, but they find that between 300 to 500 lines of code per hour is roughly optimal. But you should also never audit code for more than 90 minutes, basically an hour and a half. So it's tricky. That may help some people, those stats. I guess this slide isn't finished, but again, key thing is to be thorough, and if you start making assumptions, you can really miss bugs, or assume something is done correctly when it's not. Um, so some tips that help are to look for abstraction uh, when it's used commonly, perhaps between two developers. It can be a big source for bugs. Perhaps they don't understand each other's actual implementations or what they've abstracted out. Um, and something I saw on Twitter is something I've tried to start using more in my own code auditing, is to look for when C++ style code and library calls break down just regular old C style code. That usually indicates that two developers from different backgrounds have one has handed a project to the other, and they have two different backgrounds, and they're likely to do some stuff buggy. Um, and so also misuses of abstraction can lead to vulnerabilities, and things like JavaScript can lead to type confusion, which can cause vulnerabilities. And, um, also to focus on code patterns, especially those 4 a.m. code patterns where people copy and paste stuff and forget to tie up I guess the chunks that they copy and pasted, the variables that pertain to each one. Perhaps they, in the first chunk, do I++, then the next chunk, J++, the third chunk, K++, and the fourth chunk, they use the next variable, but in some place they use I. Um, so before we start diving into some examples, this may be a shorter lecture, but we'll have actually some exercises to do. We're going to review some stuff from last time. So we're going to cover integer signedness and promotion. So the first statement, if x is greater than y, really depends on the types of x and the type of y. If one is unsigned, both will be evaluated as unsigned. As I stated in the past lecture, that the integer promotion rules are complicated, but usually unsigned wins. I should go on the record and say that that's not always the case, and I may be wrong sometimes, because I don't understand all of the integer promotion rules. They are quite complex. So the next case, if x is greater than 16, hard-coded values like 16 are signed by default. So if x is signed and is set to a value larger than max int, it will be negative. But in the last case, you can use the capital U modifier to declare a hard-coded value as unsigned. So this will be safer because taking a very, very large value and putting into a signed integer x will lead to a signed integer error here in this case. And for a very, very large value, it may evaluate to a negative number, which may, if this is relying on a value for x, less than some value may cause a bug. Other things to consider are format strings, such as the first statement is unsafe. The second statement takes the user input or takes the string and puts it into the format string. Now, say this is %s, and we'll see this here. So if the input has conversion specifiers itself, let's say this is %d or %x, okay? What we're doing is we're printing into temp a string formatted by this, and it's reading another string into this, and that's what it corresponds to. So what it's going to do is put this in there, move to the next character, and regardless of how many characters this input took up, the conversion specifier algorithm starts immediately after it and continues going. Now it's going to see this as the end of string, so it's not going to do anything more. But any conversion specifiers listed in here remain intact. So if there's conversion specifiers that happen to be put into this last printf, those will actually cause perhaps bugs or integer, format string exploit. Another interesting category to consider, off by one errors. For instance, if you have a character array that's 5 long and you go up to equals 5, that's going to be 0, 1, 2, 3, 4, 5. That's going to be 6 characters that you're going to be iterating over. So it should have just been less than 5. Other example cases, incrementing too many times or improper calculation of bounds, and I should reiterate that size of does not in fact equal string length. Size of returns the number of bytes that are used to store that variable. A string length returns the number of characters up to and not including the null terminator in that variable. So it'll be at most size of -1. It's very important to consider. So I guess I didn't cover this, but for those who maybe needed this refresher, the I++ versus ++I behavior. In this statement, any use of a variable that's such as I++, it will evaluate the statement first and then do the increment afterwards. But if you precede the variable by ++ or minus minus, it will do the increment or decrement respectively first and then evaluate the rest of the operation after that increment or decrement. This slide may be a little out of place, so bear with me. When processes are loaded into memory, they are broken into many small segments. But the main ones are the text.txt section, and this contains the machine instructions. So it contains everything that results from compiling the code. All those instructions get put here, but the data, like declared global variables, get put actually in other segments. And variables that are used in runtime dynamically or statically used are put in other sections as well. For instance, the .data section contains globally initialized variables. The .bss section contains globally uninitialized variables. The heap, that's for dynamic memory management. The stack, that's for other memory management stuff that's already instantiated that are local variables, not global and locally declared variables. So there are some general causes for bugs, basically involved in the way things are implemented, failure to validate input, failure to understand API miscalculations, failure to validate results or check errors or application state failures. Perhaps they were caused by complex protocols, complex file formats, complex encoding, decoding, etc., etc., etc. But really, a lot of that is just noise, and I found it more useful to focus on categorizing bugs and focusing on bug categories as opposed to just a heap of general strategies. Um, we did cover the seven kingdoms in the common weakness enumeration document provided by Meter at the beginning. MITRE, sorry. And that's very useful. You can come up with overall strategies for attacking those, but the list I have here comes from a Black Hat presentation in 2006, and they roughly correspond to those the seven kingdoms that were described earlier. But these are often these four are often the heavy hitters for binary application bugs, which are the topic really of this week in today's lecture. So the first category are API-based bugs, and we've pretty much covered this: dangerous use of safe functions or use of unsafe functions. Um, and then there's programming construct errors, which are really described by bad development practices and involve integer assignment bugs, integer boundary bugs, logical bugs, boundary bugs, using uninitialized variables or not checking the return codes from functions or checking the value of variables. State mechanics, such as bugs where the process is left or the processes are left in an inconsistent state. We've discussed this with concurrency issues and deadlocks. It also pertains to global variables and also privileges. And we'll cover privileges more in the next lecture. There's also, as these authors from this Black Hat presentation describe as external resource interaction, where really it has to do with dangerous interaction between various different components in that architecture. Perhaps the web server and the database don't interact safely, or perhaps there's an LDAP, dangerous LDAP interaction that leads to directory traversal or accessing protected things. And often this is exploited by a class of bugs I consider, or vulnerabilities I consider meta-character injection, and that really different languages, or rather interpreted languages, usually such as the web server is running PHP interpreter or Python or Perl or CGI, have different meta-characters that trigger parsing to behave different ways, whether it starts parsing data as now, okay, the rest of this following this character is now a command, or whether this is a new string, or whether this is a directory traversal meta-character. And meta-character injection applies really when applications interface with the various components of that architecture in a dangerous way. Sometimes these components are they're passing off a calculation to the shell, or they're passing off to a library that's perhaps written in a different language, or they're passing off to the database. And it's really important when auditing for meta-character injection to understand how each component handles their meta-characters, and to understand and to focus on how bugs can be introduced in the interaction between these components. So there are some important cases like dot dot, string, start, and closure, wildcard symbols like star, percent, union commands, or representing next command or ending this one, starting another one. comments sometime if you can inject them in SQL. You can comment out the rest of a query, which perhaps would restrict it to perhaps unprivileged users. And we'll explore that more later. So let's start going into some examples, because a code auditing lecture wouldn't be really worth anything if it didn't have some examples. So there is an integer overflow, well, rather bug, in this example. If you haven't spotted it by now, what I'm going to do for each example is I'm going to give you time to pause the video, and in about 10 seconds I'll explain what the bug is and how it would be exploited, or perhaps how it could lead to exploitation. So in this case, what we're taking in is an integer, and we have this temporary value that's being a short, and we're putting the integer into a short, so that's truncating it. So that's losing information, and perhaps we're looking for things that are greater than 1024, and if that's the problem, we'll return 1. Well, if the lower half of the integer, the bits, don't evaluate to greater than 1024, we're cutting off all this most significant half. So that could lead to dangerous cases being evaluated as safe. So the next one, I can give you time to pause. So the error here is that essentially we're taking an integer, and by default they're signed, and we're comparing it here to a pound define, max stock buff. By default, pound defines are also signed. So we're comparing signed versus signed. So usually the first 4 bytes in, say, a 32-bit system on the socket buffer are going to denote the length of that packet to read in. So if that's the first thing we read in and say it's extremely large, and the most significant bit is set, then it's going to evaluate to a negative number. So in that case, we may end up reading a very large amount. So if you send it a very, very large packet, at the end of the day, it will cause a crash and perhaps lead to potential exploitation. So the question is will read still work because this is a signed integer? And effectively, yes, it's going to get typecast to size_t. And so it's going to get used as unsigned integer in the function. And that may be compiler dependent, but in most cases it's not. So here's the next example. So the vulnerability here, this is actually from a CVE in a open source SSH application that was trying to detect CRC attacks. And this is some of the actual source code. Obviously, we've cut out the stuff that's not relevant to this actual vulnerability. But what's going on is that the very first variable is a function pointer. And we declare word 16, word 32, word 32. You may not have seen these before, but it's effectively describing that this is going to be 16 bits, this is going to be 32 bits. So if you needed that hint to perhaps get a little further and actually find out the bug, go ahead and pause it and keep going. But if you didn't, the bug is effectively that there's an integer truncation here, that we're taking a 32-bit variable and we're putting it into a 16-bit variable, then we malloc a chunk on the heap that is n times the size of 16-bit words, so n times 16 bits that are going to be used for calculating the result of this CRC attack detection. And what's going on here is that it keeps going on the heap until the index is used. So effectively, it keeps writing whatever j evaluates to. You see j is declared here, and it's iterating up j++, and it's not used in anything else. But it keeps going and going and going until this is satisfied. However, the problem was that it should not have truncated this, as it mallocs too small of a size. So that leads to memory corruption that can be used to buffer overflow the adjacent heap chunk. And we covered last time on how that can be subverted to lead to an arbitrary write. So covering buffer overflows is very simple. We've talked about this a bit. This is a very simple demonstration of putting too large of an item into too small of a space. You're going to corrupt the adjacent memory. And there are ways to do this. Obviously, this is API abuse, using a safe function improperly. But it's also important to note that some safe functions have to be used with more focus than other ones. Obviously, in this case, the proper way to do this is with stir length of the destination buffer. The problem here is that this is going to start the second stern cat on the first null terminator character it sees. So if that's all the way at the end or over halfway through the end and it starts printing all this extra stuff, it can corrupt the adjacent memory, as it will write out of bounds. All right, these are very simple, and obviously it's 3 lines of code. That's hardly useful. It doesn't give you any real experience, and obviously I'm giving hints. So the remainder of the class is going to be you pausing the video when I get to the code example and trying to find the bugs, and then you can unpause it to find me explaining how they manifest and how they work. So if you've identified the bug, to explain what's going on is that it has declared a character pointer and there's a buffer, and it set the character pointer to the very beginning of the buffer, and it's also set a character pointer to the very end of the buffer, which is declared by the size of the buffer -1, and that's the very, very last byte of that buffer. And whoops. And what it does is it takes in input and it checks to see if their input is characters, and then starts reading in, basically using the character pointer PTR into the buffer, the input characters. And what it's doing is it's checking in the switch for special characters. And what is actually the bug is an off by 1 error, in that it increments this twice. Now, this normally isn't a problem unless the character pointer is right at the end. And if it increments it twice, what's going to happen is that this loop check that keeps going until the pointer matches the last byte will never evaluate to true. It will actually be past it, and it's going to keep incrementing. And so it's going to keep writing whatever characters it gets at that pointer and continuously corrupt the memory until it no longer gets characters. Rather simple example. And the above is the source for the code. And you can find more source code auditing examples at this lecture. Now here's the next example. There are 3 vulnerabilities, so do take some extra time with this. So the first vulnerability is actually this line of code here. It is using this function, this safe API call, but however improperly, because it's telling it to write size of buff, which is going to tell it to write 16 characters, and the very last character should be reserved for a null terminator. However, if this is larger than 16, or in other words, if there's 16 characters in a row and none of them are null terminator, this will carry out the stern copy and there will be no null terminator at the end of the string. So whenever it's used or ever used to evaluate, it can continue reading, and if it's used to stir copy or do any form of memory copy, it will lead to memory corruption. So that's the first vulnerability. The next vulnerability is that we take in user input and we convert it to an integer and we store it in an integer len, which is again by default signed. And so we compare a signed to a signed, and so if this is sufficiently large that the most significant bit is set, we will then copy a very large amount, because this will be evaluated as an unsigned within this function, to the destination buff2, leading to memory corruption. Now the next bug, you may have guessed, is stir copy, but that would be wrong. This is actually a safe use of stir copy, copying a static variable into buff2, and uninitialized with the null terminator on that is smaller than the destination. The bug is actually in syslog. This line is actually a format string function, and this denotes the type of error. It's an integer or number-based character type, and the buff should have been preceded by a format string. So if buff contains any conversion specifiers, that would enable a format string vulnerability in the syslog function. Now how that would be used is that in argv3 this would have to contain conversion specifiers, and this function snprintf, it takes in the destination, the amount of characters to use, which again, that length check, this is being used as unsigned, so it's potentially also a vulnerability here, leading to a unsafe use of this API function that results in a buffer overflow. But that really is the same bug, and it evaluates this format string and then inserts this there. So if this is then printed to the log in an unsafe way, any format string conversion specifiers that are put here will invoke the format string conversion handler here in the code for syslog, leading to a format string vulnerability. So like I said, considering the unsafe check of a signed versus signed in a length check logic, and considering this and that really the same bug, you can debate me on that, and um, it can be correct to say that they are different bugs, because you'll see that often when patches come out to fix something like this, they may forget to fix the use of this, and they'll typecast here unsigned or 16U and rely on the integer promotion there. However, it can lead to obviously the buffer overflow if it's used in this manner. So that leads us to our last set of code. Fortunately, this is spilling over in the display, so let's do that. Okay, go ahead and pause it and try to find the two vulnerabilities in this code. So, hopefully you found them both. The first vulnerability is this second stern cat, as they're both writing to buff 3, and obviously stern cat looks for the first null terminator, and that's if these are both sufficiently large, will cause this to write more characters than there are in buff 3 into the address space, corrupting adjacent memory. Now, you may have thought that this might be the second vulnerability, as it is executing a shell command and is passing in user input directly as an argument, and perhaps you were thinking that it could do semicolon and then cat etc password or do something. In fact, it has actually a safe use of it, as the argument variables are going to get evaluated in a safe fashion. However, you'll see that later on we are also calling a different function. And what's going on here is that there's an attempt to filter out some meta characters. So we're filtering out ampersand, tildes, semicolons to prevent stuff like that, and ors. And then what we're doing is we're creating the command string to cat out some function, some file rather, and we're passing into this format string argv7, and then we're calling it with system. So this is not a format string vulnerability. In fact, it is actually just improper validation of input, in that all you have to do to see how this would manifest improperly would be to submit for argv7 my password file, and then cat into the greater than symbol, etc password or something like that to overwrite a file. In other words, to do redirection. The character is this greater than symbol. So that these examples, these two, are from Jared DeMott's Source Code Auditing 2008 presentation at Black Hat, and he has other examples in his slides. And this may be a shorter lecture, and I've released the homework. It's due next week, and I don't expect you to think this is a comprehensive coverage of bugs, comprehensive coverage of source code auditing, but for C and our focus on it and the limited amount of time we have, it's really the best I can expect you to understand without heavy C experience. And so that is the end of the lecture. Feel free to send me your questions.